Last year, I registered as a bone marrow donor. If any of you have done that, you'll know it's a very simple process. You spit in a cup, fill in a form, and one day, you may save a life. Why? Because the bone marrow contains stem cells that can regenerate a whole blood system, and these cells are routinely transplanted to help people with leukemia. But here's bad news. It's not always easy to find a perfectly matching donor. And so 1 in 3 people after receiving the transplant may suffer from life-threatening complications. So rather than getting everybody spitting in the cups, there must be a better way to help. Imagine, if we could take skin cells from the perfect donor, the patient themselves, and play with them in a dish to reprogram them to become very efficient, personalized blood stem cells for transplants, that would be great. But we can't. We can't, because we can't simply make a blood stem cell with a click of fingers. The whole process of making a stem cell is more like a marathon run, thousands and thousands of steps. Now, each of these steps results from the action of genes, the carriers of information and instructions in our cells, made up of the DNA, which Emily just told us about. The genes have specific roles. They work together and form networks to make sure that every cell appears when and where it has to. The gene that I'm looking at in my PhD is called GATA2. And GATA2, for a blood stem cell, is a bit like food for a marathon runner. If you haven't had enough, you're probably not going to finish. But if you've eaten too much, you're going to struggle as well. So I'm investigating why a blood stem cell needs intermediate amounts of GATA2. And to understand this, I'm looking at probably the most natural setting, an embryo that is making the blood stem cells for the first time. But don't worry, I'm not using human embryos. I'm using fish instead, the zebrafish. Although the zebrafish looks quite different to us. The way their embryos make blood stem cells is almost exactly the same way to the way we do it. So, I took my fish, played with their genes, and made embryos that have either too little or too much GATA2, and they don't make blood stem cells. And I'm looking at what changes in these embryos on a very molecular genetic level to better understand the function of GATA2 and explain its importance in a wider context. And the motivation is that maybe one day we can use this knowledge to replicate the whole stem cell marathon in a dish, step by step. Although my research may only explain few of the steps, if the research around the world goes hand in hand, maybe, if any of us ever needs a bone marrow transplant, we won't need to wait until somebody spits in a cup.